In this video, we will start section 3.1.2, linear systems. We will define many terms related to linear systems and solve several linear systems using high school methods. First, we have definition 3.1.3. A set of m linear equations in n variables is called a system of linear equations, or a linear system. The vector s1, s2, up to sn is called a solution of a system of linear equations if it is a solution of every linear equation in the system. Solving a system of linear equations means finding all solutions of the system, and two linear systems are called equivalent if they have the same set of solutions. In example 3.1.3, we are asked to solve the following linear systems using high school methods and interpret the solution geometrically. In part A, we have a system of two linear equations in two variables. The two variables are x and y. Solving the system means finding x and y. From high school, we remember that we can add or subtract equations in the hopes of eliminating variables. Let's do that here. We see that if we add the two equations, we will have eliminated the variable y. On the left-hand side, we have x plus 2x, which is 3x. On the right-hand side, we have 4 plus 2, which is 6. And so we can solve for x. X is equal to 2. We can now plug in this newfound value of x back into either equation and solve for y. Let's take the first equation. We have x plus y equals 4, and so now we have 2 plus y equals 4. Solving for y, we get that y is equal to 2. And so we found the solution to the system. The solution in vector form is xy equals the vector 2, 2. Let's now interpret the solution geometrically. Each of our equations are linear. A linear equation in two variables is the equation of a line in R2. We know how to graph lines in R2, and it becomes easy once we solve for y in each of the linear equations. So x plus y equals 4. If we solve for y, we have y equals 4 minus x. And so this is a line with a y-intercept at 4 and a slope of minus 1. And that one is actually already drawn. What about the red line? If we solve for y in the equation for the red line, we have y equals 2x minus 2. And so this line has a y-intercept of minus 2 and a slope of 2. There it is. Now, the geometric interpretation of the solution is that the two lines intersect at the point 2, 2. Two lines intersect at 2, 2. In part B, we have another system. The first equation is the same as the first equation of the system in part A. The second equation is now different. Second equation is 2x plus 2y equals 6. Remember that multiplying an equation by a real number doesn't change the solution of that equation. Let's multiply the second equation by 1/2. That'll give us the new equation x plus y equals 3. We're going to keep the first equation as it was. And what we have now is an equivalent system. Now if we subtract the second equation from the first in this new equivalent system, we obtain that 0 is equal to 1. Clearly, this is inconsistent. And so the system of linear equations actually has no solution. Let's now graph the red line. X plus y equals 3. We can rewrite as y equals 3 minus x. This is a line that has a y-intercept at 3 and a slope of minus 1. And we see that the two lines are parallel, distinct. In part C, we have a third system. The first equation is still x plus y equals 4. The second is 2x plus 2y equals 8. Again, we'll multiply the second equation by 1/2. We then obtain a new system of linear equations. The second equation is now x plus y equals 4. And the first equation is x plus y equals 4. This new system has two identical equations. We only need one of those equations to describe the solution set of the system. And so this new system with only one linear equation is an equivalent system. We cannot eliminate any of the variables, x or y. What we'll need to do is set one of the variables equal to a parameter. We'll set y to be equal to t, where t is any real number. And then we'll solve for x in terms of t. So we know that x plus y is equal to 4, so x must be equal to 4 minus y, or 4 minus t, since we've just set y to be equal to t. We can now write the solution set as x, y equals 4 minus t, t for any t in R. And so any value we choose for t to plug into the vector 4 minus t, t will give us a solution to the system of linear equations. This means that the system has infinitely many solutions. What does this look like geometrically? Well, the two equations trace out exactly the same line. The red line is the same as the blue line. And we see that the two lines are coincident. What we've seen from the three systems we've solved so far is that linear systems can have one solution. They can have no solution at all. Or they can have infinitely many solutions. Now, are these three cases the only possibilities? It turns out that yes, they are the only possibilities. Before moving on, we need to define two more terms. Linear systems with one or infinitely many solutions are called consistent, and linear systems with no solutions are called inconsistent.